I start recording now. Can you still see my screen? Seems not. So if we recall the last formula we have seen in the ideal gearbox, and we set the load as a pure inertia load, which means that we don't have any external forces applied to the load. It will just be the inertia GL. Then we have a TL equal to 0. Then we can write this inertia matching formula, which is assuming TL equals 0, inertial load. Then this formula was giving us TE equal GM plus gearbox squared times GL. And d omega m, which is the same as omega m divided by omega L times d omega L dt plus 0. And this is equal to 1 divided by the gearbox, omega m divided by omega L. So that gives us TE equal GM plus gearbox square GL times 1 divided by gearbox times d omega L dt. And if we put this 1 divided by gearbox inside the parentheses, we have an expression TE equal to GM divided by gearbox plus gearbox times GL d omega L dt. And if we plot this function, so TE, so the required motor torque TE, and if at a given acceleration, load acceleration, d omega L over dt. So if you want to accelerate the load for a given acceleration, changing the gearbox will give us a different value for the required torque from the motor. And if we look at this function of gearbox as a parameter, it looks like when the gearbox is very small, then the first term on the parentheses is very high. But then when the gearbox is increasing, the first term is decreasing, so it goes down. And then when the gearbox is very high, the second term becomes very high. So we come to a minimum and up again. And this is this minimum here that we want to find, because that will define the optimal gearbox ratio, optimum, that will give us for a given load acceleration the minimum motor torque that is required. For a given load acceleration, we want to find the gearbox ratio that minimizes the motor torque. Or I can say it on the other way. If I choose a optimal gearbox, then I will have the maximum acceleration available for a given motor. Because if I have a maximum torque for the motor, using this maximum torque and the optimal gearbox, I will be able to have a very high acceleration on the load. So that will maximize the dynamic of my system. So how do we find a minimum? Then you probably know we take the derivative of the function and we look at which gearbox the derivative is equal to 0. So if we take dte over dt, that will be equal to 1 divided by x. The derivative is minus 1 divided by x2. So gm divided by gearbox squared. Derivative of a linear function is just a coefficient plus gl. And also, sorry, it's not time, it's gearbox. I differentiate it against the gearbox is a variable, digb here. So this is the derivative of omega L on time is independent on the gearbox, so it's the constant. And this is equal to 0 if the term inside the parentheses is equal to 0. And this term inside the parentheses is equal to 0 if we have the gearbox equal to the square root of gm divided by gl. Because if I take this, then I have minus gl plus gl equal to 0. So it cancels the derivative, and that will be my optimum gearbox. So IGB optimum equal it has to synchronize, it's just a bit slow. Yeah. So that's equal to square root of gm divided by gl. Which means that if IGB equal to IGB optimum, then I can write by the gearbox ratio squared times GL equal to GM. And that means if we look at the formula here, it means that we have matched the inertia, meaning that the inertia of the load referred to the motor side, which is IGB squared GL here, that would be equal to Gm, the inertia of the motor. So we have a matched inertia. So that's why it's called inertia matching. And that's what will optimize the dynamic in a motor drive chain. So that's the conclusion. If Jm equal to IGB squared GL, then we have inertia matching and we have highest dynamic. Okay, I will go a bit faster now for the non-ideal gearbox. If you don't have any questions, I will. So I stopped the record for the inertia matching video, and then I will start the new video, which is on the non-ideal gearbox. So let's start the recording now. So for non-ideal gearboxes, it means that we will have some friction between the sliding tooth surfaces, and we can use efficiency coefficient eta, which is between 0 and 1. So if eta equal to 1, it's ideal. If it's less, it's none. It's not. And then we can also add some viscous friction on each side of the gearbox. And that will be parameterized by mu1 and mu2. And these are the viscous friction for the motor shaft and the viscous friction for the load shaft, respectively. Then, when I move the inertia to the motor side, instead of having the gearbox ratio squared times GL, then I need to divide by the efficiency eta. And then I will add a force, which is proportional to the speed with coefficient mu1, so mu1 omega m. And then the other viscous force from the other side that will be referred to the motor side, I multiply also by the gearbox ratio squared. And divide by the efficiency. So each time I move from one side to the other, I divide by the efficiency eta. So the last term is also the external force or torque, sorry, applied to the load, TL, referred to the motor torque. I multiply by the gearbox ratio and divide by eta. So I can, maybe to make it clear, I can draw this on the graph. It's GM inertia. And here we add a viscous friction. with coefficient mu1. And then we have the gearbox. And this has a efficiency of eta. And then we have a new friction, viscous friction on the other side with coefficient mu2. And then we have the load here. And we have TL and TE. And then we also have, here we have T1, and here we have T2. So if I look at my first gear, I have Gm d omega m dt equal to Tem minus T1 minus mu1 omega m. And then on the other side, I have Gl d omega L dt equal TL plus T2, same as before, but then we need to add minus mu2 omega L. And because we don't have a not ideal, then this time I have omega m T1, which is not equal to omega L T2, but it will be equal to omega L T2 divided by eta. And that's why we got at the end this formula, which I show you on the PowerPoint. So if we combine these three equations, then I have Gm times omega L omega m squared times, you can double check this at home, d omega m dt plus mu1 omega m plus mu2 omega L omega m squared omega m divided by eta minus omega L divided by omega m TL divided by eta. Okay, and then I stopped the recording here. Okay, so now we have 45 minutes to look at simulation in MATLAB. How can we simulate this? And that will be used later on the project. You will have to do some simulations in Simulink. So let's simulate this winch first. And I will start the recording again. If you don't have any questions in between, I don't see anything on the chat. So I will keep. So let's start the recording, yes. So the question in this video is how to simulate, for example, a winch mechanism. In Simulink, so we will start with the equations. We have a motor which is operating a winch with TEM as a torque. Winch has a radius of R and inertia Gm. And we have a mass with mass M attached to the end of the rope. So we have a force mg. If we take Newton's law for the motor shaft, then the acceleration times the inertia is equal to the applied moment, torque, sorry, minus the force times the radius. And if we look at Newton's law for the mass m, so we have mass times the acceleration, the linear acceleration, which is r times d omega m dt, is equal to the force of the winch to the mass F minus the weight m times g. So we can put these two together and we will get inertia plus r square m times d omega m dt equal to the moment of the motor minus TL, which is r mg. So let's look at Simscape. And in this example here, we will have so the same example as in the slides with GM equal to, I will put some values, 4 kilogram meter squared. That's for my motor, inertia, GM. And then this is attached also to the winch. We have a radius R. Let's take 0.25 meter. And then we can model the wire by spring and damping. So here I have a spring plus a damping with a K equal to 1E8 Newton per meter. And the damping ratio, which is 1000 Newton second divided by meter. And this wire is attached to a mass with mass M equal to 10 tons, so 10,000 kilograms. So the method is to open MATLAB and then create a new Simscape model. And in MATLAB, you do it by typing, so that's MATLAB prompt. You type SSC underscore new. So let's try this. I open MATLAB. I have a 2020A version. So please, if you have 2021, it's okay. You will be able to open my files. But if you have 2019, you should upgrade to 2020A at least. And then let's open a new MATLAB window is here. So what I did, I created a parameter file, a .m file, where I put my parameter definitions. So I have the mass, the damping, the stiffness of the wire, the radius of the drum, gravity, and inertia of the motor plus drum. And then here, as I said, ssc_new. Then it will automatically open a new window, which is pre-made for Simscape. So it looks like this. We already have a Simulink to physical system converter. We have a scope, but I don't use a scope usually. And then we have a solver configuration. And then we can find the component in the Simscape library. So let's add the components. So I will have a winch, which is called a rope drum. So that's my winch here. And then I have the wire. I will use a translational spring. And a translational damper. So that's for the spring. The spring rate was K. And here my radius was 0.25. No, I should use R. And then the translational damper, which has a damping coefficient equal to D. Then I need a mass. And the mass is equal to big capital M. Yes. And then I need this gravity. And this gravity, I will use a constant, which is minus mg. Minus m times j. Which I convert into, so that's a physical signal. And I make it a Simscape signal by using this converter here. Okay, it doesn't work because maybe I don't have the definition of the parameter yet. If I run this parameter definitions here, then I will register the values. Okay, I just made a mistake. It's a Simulink to physical system. It's not physical system to Simulink. And then I need to generate a translational force. And this is done by a force source. So then I can connect this. And now I have my gravity that I need to attach to the mass. And this is a wire that is attached to the spring and the damper. And this wire is attached to the drum here. And the other side of the drum, I can just put it a free rotational. No, sorry, translational, free translational end. Translational free end. Okay, now I need to attach the motor to the drum. So for this, I will use an ideal torque source. And then, yes, I need to add to attach the solver to one of the line of my Simscape model. So it doesn't here. It can be wherever. It can be here or here. I choose here, but it has to be somewhere. Then what I want maybe is to measure now the position of the mass. And for that, I need a motion sensor. Ideal translational motion sensor. Initial position 0. I connect this to the mass, and then I will know the position of the mass by P is the position, V is velocity, and C is a reference. So actually, let's measure the velocity. And I need a reference, which is a mechanical translational reference. And that gives me the speed of the mass. So if I want to control the speed, for example, of the winch, of the mass attached to the winch, I can have some as an input reference speed. And let's take a repeating sequence. So what we have done is we have assembled the physical component, which is the winch, the motor, the MAS, and the wire. And then we want, for example, to give to have a desired velocity. That looks, for example, like this. It goes at time steps. Every second, something happens. T in seconds. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it goes from 0 to 1, and then from 1 to -1. V in meter per second. So for the first 2 seconds, it's 0 speed we want. And then we want it to increase to 1 in 1 second. Stay at 1 meter per second for 1 second. And then decrease to 0 again. And then to -1 after 2 seconds. And then stay at -1 speed. And then increase back to 0. At 9 seconds. So then we can go back to MATLAB and have this repeating sequence. Which is a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So at 0, we have 0, and then at 1, we have 0. At 2, we still have 0. At 3, we have 1. And then it's 1, and then 0, and then -1, and then -1, -1, 0. So that will look like this. Yes, that's what we want. Or was it? Yes, it's go up and down, and then it's repeat. And you know, if you want to control the speed, then we need a closed loop. So we measure the speed and compare it to the desired one using a sum, which will be nothing plus minus. And then we can use a PID. And then we need this converter from Simulink to physical. And this gives us a torque, so we need a reference torque source. No, a rotational reference. Rotational reference. So let's attach this to the measured speed. And then we can log some signals. So for example, vref, I log it, I right click here and log the selected signal. And then this is my measured speed, v measured. And I also want to log this. Okay, so now if everything is correct, that should simulate my. So let's tune the PID. I will just do it a quick way. So which is I double click on this. I choose PID, yes. And here it's 110, but if I have auto tune, then I just click on tune. And I have an error message that says that my initial condition solve failed to converge. So maybe we need to give some values here. No, I don't manage. Okay, I need to double check a bit here. I have K and D, the drum, which is R. If I look here, I have, yes, a small viscous. Yes, I need to add the inertia on my drum. If you don't have inertia, then you will not be able to simulate it, yes. So here I have, that's where I enter my GM, which was given, apply. So now I have inertia, so you cannot simulate without inertia. Otherwise, yes, it gives you some errors. So let's try again now to tune this. Oh no, I have still the same problem. That's correct. Maybe I can try with another solver, but I can simulate for 30 seconds. Because now if I run, I will get some strange results because I haven't tuned my PID. Yes, and I got an error saying algebraic equations. I have to find what is the bug here. Oh, I need a mechanical reference here also. Yes, maybe that was it. Let's try to tune again. Yes, so now I have it. Yeah, so it's easy to forget one small reference and then the whole simulation is not running. But then here I can, for example, choose my frequency, the phase margin, so 60 looks good. And then, so it will auto-tune here in less than 100 milliseconds, it will reach maybe the setting time. So that's good. I can update the block. And now I can run my simulation. I have to close this first. Okay. And yes, I have two questions. Does the bottom ideal for source need input on C, like the ideal source torque source? So no, we need to have the input on the S and the reference on the C. So I do the same here. S is a force, and then C is a reference. is C port in the ideal force source should be free. In the ideal force source, no, it gives you a force, and you need to fix. You need to have a fixed reference, not a free reference. Yes, okay. You had some suggestion for errors, but yeah. So now everything is working, and look at the results. We look at the log, and this we go to the data inspector. Which give us pretty good results because of the tuning of the PID. So if I have the V measured and the VRF, so that's my VRF. If I remove it, and then the V measured follows the desired speed quite closely. And we see a small overshoot, and that's what we expected from the PID. Okay, how much time I have left? I have 10 minutes left. So I will share these files in Canvas. But let's look now at a pulley, because that's you will need to have a pulley in your project, or maybe several. And the problem with this is that we don't have a block in Simscape for a pulley. We just have blocks for winch that cannot move up and down, but we need a pulley that is actually the same as a drum, except that it can also move up and down. About the equations, we don't have any inertia in the pulley, so the force F2 is equal to F1. And here, if we consider, we don't consider the stiffness and the damping, F3 will be equal to F2. So we can write the two equations that we had before. And then write the final, which is equivalent inertia times acceleration equal TEM minus RMG divided by 2. We have divided by 2 now because when the mass is moving 1 meter, the wire here needs to be wound up 2 meters, because you have a length on the right and a length on the left. So we need twice as much wire displacement to get displacement of the mass in the middle. So it's the same as having a kind of a gearbox with a gearbox ratio 1/2. So here we need to divide by the gearbox ratio 1/2, and here by the gearbox ratio squared, which is 1 divided by 4. So that's why we got this 1 divided by 4 here and 1 divided by 2 here compared to the previous example. But as I said, we don't have a pulley in Simscape. But we can fix this. By loading some custom components into Simscape. And again, I have to close this and open it again to synchronize the file. And I created already some custom components like a pulley. And I will give you a file for this, but what you need is to load them in Simscape when you open your model. And you do this in MATLAB, when you have the prompt, you write ssc underscore build. And the library that I created, it's called custom component. It's important to have a capital C and capital C for component. and a S here. And even if what I will give you in Canvas is it's a map which is called plus custom components, but here you don't need to have the plus. Don't write plus before custom components. So let's show you on MATLAB. I can close that. If I so what you will get is this one plus custom components. And if I remove this one, and here I put SSC build custom components, then it will, you see, it creates this lib file. And now, so now it's done. And if you go to here, and if you go to the Simscape library, it should populate somewhere. It should create a new library here. If I go to library browser, come back here. Well, what we can do is to open this this custom component lib SLX. And then you have the components here that you can drag. Or actually, you just have one here. So that's one component that is custom. You can drag it here. And that will work as a pulley. So I will let you use it in the tutorial and see if you manage. But yes, so that was a simulation of rotating system and coupling a mechanism. Like we can also have a gearbox. Gearbox, yeah, if needed. Yeah, so that's the main components that you will need in the project, and also generally if you want to have a rotating mechanism. We have a few minutes, 3 minutes left. If you have questions, I will stop the recording first. Yes, it's not recording anymore. Yes, I had this last slide. That will be also useful in the project or in the last lecture, lecture 9, on how to find what is a mean power that is needed when we have a duty cycle which is not continuous. So here we have a 4 kilowatt for 2 seconds, and then nothing, and then 2 kilowatts, nothing, and then it's repeating. We are not going to consider the mean of the power to size the motor, but instead we need to find the RMS power, which is a mean of the squares. So we square this duty cycle, which is 16,044, take a mean of it, which is 5, and take the square root of 5, which is 2.24. So the continuous power rating in this case will be 2.24 kilowatts, and not 1.5 kilowatt if we had taken the mean of the power. Okay, question here about the project. When does the project start? It says in the teaching plan that it will start when we are done. So after 9 weeks of lectures and tutorials, we will have 5 weeks of projects. So double check on the teaching plan, which is in lecture 00. It will start, the data is given here. Okay, so next we will have a small break of 15 minutes. And then we will come back in a Zoom meeting, but it's another Zoom meeting address. And here we can, depending on how many we are, we can make a breakout rooms if needed. Yeah, we will see. And you can start answering the tutorial, and I will help you if you get stuck somewhere. And we will have 3 hours of this tutorial. Okay, I will end this meeting now. Thank you for your participation and the questions you had. And see you in 15 minutes for the tutorial. Bye.